Agricultural states dependent on river systems required stable coordination across measurement, storage, and redistribution. In the Nile Valley, annual inundation followed a recurring pattern, yet its magnitude varied from year to year. Productive agriculture depended on anticipating flood levels, recalibrating field boundaries, and aligning labor with seasonal constraints. Stone construction, grain storage, and taxation in kind imposed additional demands for consistency across space and time. These conditions created practical problems of measurement, alignment, transport, storage, and load distribution. This is before logic, a history of rules before they were written. Long before formal deductive systems were articulated in writing, Egyptian administrators, surveyors, and builders operated within tightly constrained material environments. Surviving documents and structures indicate that procedures for calculation and planning emerged in response to these constraints rather than from abstract theoretical inquiry. The mathematical papyri that remain, most notably the Rind mathematical papyrus and the Moscow mathematical papyrus, provide evidence of procedural techniques rather than axiomatic systems. The problems are presented as worked examples, followed by ordered computational steps expressed rhetorically. They include methods for calculating areas of fields, volumes of granaries, and capacities of cylindrical or truncated solids. Fractions are expressed primarily as sums of unit fractions, and standard decompositions appear to have been memorized and applied systematically. There is no surviving indication of formal proof in the later Greek sense. Instead, solutions are demonstrated through repeatable procedures that yield operationally sufficient results. Geometry appears as an instrument of land measurement and construction, rather than as a deductive discipline organized around definitions and theorems. Within these texts, checking procedures are frequently embedded. After a calculation is completed, the scribe often performs an inverse operation to confirm the total. Multiplication may be followed by division to verify proportional distribution. Addition may be restructured to confirm balance. In a subsistence economy where miscalculation of grain rations or taxation could produce material instability, such reversibility functions as a safeguard. The procedure does not eliminate error in principle, but it reduces propagation. The structure resembles a zero-error protocol within the limits of available arithmetic, ensuring that deviations are detected before redistribution occurs. Error management, rather than theoretical elegance, defines the priority. Engineering projects from the Old and Middle Kingdoms further illustrate optimization under constraint. Monumental architecture, including pyramids, temples, and administrative complexes, required stable foundations, predictable load transfer, and precise orientation. Archaeological study of quarry marks, ramp remains, and unfinished structures indicates iterative adjustment in response to material limitations. Stone blocks were shaped to standardized dimensions suitable for coordinated placement. Transport systems appear to have minimized friction through sled design and lubrication. Internal chamber systems in pyramids redistribute weight away from vulnerable voids through relieving structures. The resulting forms are stabilized solutions within known tolerances of stone, labor organization, and available tools. Surveying techniques, likely involving cords, plumb bobs, and sighting instruments, permitted alignment with cardinal directions at a degree of accuracy that continues to be examined. These practices required consistent measurement standards and calibration across teams. Standardization enabled modular planning. Repeated block dimensions allowed different labor groups to quarry, shape, transport, and place materials in parallel without continual recalibration. When units are interchangeable within a known tolerance, sequencing becomes predictable and coordination overhead is reduced. The architectural plan can be decomposed into repeatable modules, each executed independently yet fitting within the whole. This does not imply abstract project management theory, but it does indicate structured constraint sufficient to scale construction across thousands of workers. Regularity in material units reduces variance and stabilizes cumulative structure. Administrative records from later periods show a bureaucracy capable of tracking grain storage, labor quotas, and taxation in kind. Hieratic numerals and accounting marks enabled aggregation and redistribution at scale. The Nile's annual flood both erased and redefined property boundaries, necessitating recurrent surveying. Classical sources describe rope stretches. Direct evidence is limited, yet the centrality of area calculation in extant texts supports the practice of remeasuring fields after inundation. In this context, optimization refers to maintaining equilibrium between environmental variability and institutional demand. Storage capacity had to match anticipated yield with allowance for spoilage. Construction timelines had to coordinate with agricultural cycles. Labor mobilization depended on predictable administrative rhythms. The structure of Egyptian mathematical texts reflects this orientation. Problems are concrete, embedded in scenarios involving bread distribution, beer production, or land parcels. Methods are presented as ordered procedures labeled as correct reckoning. Abstraction is present but implicit, embedded within standardized problem types rather than stated as general principles. Scholarly interpretation varies regarding the extent to which underlying mathematical concepts were explicitly articulated. The surviving record is limited and mediated through copies produced centuries after initial composition. Nevertheless, consistency across documents suggests a shared professional culture of calculation and verification. Construction techniques reveal systematic management of material constraints. Limestone and granite differ significantly in hardness and fracture behavior. Tool marks indicate adaptation in chiseling methods depending on stone type. Mortar composition and joint tolerances vary across periods, reflecting adjustment to structural demands. In pyramid construction, internal relieving chambers above burial rooms redistribute vertical loads to prevent collapse. Early structural failures, visible in the archaeological record, appear to have informed subsequent design refinements. Optimization operated through accumulation of empirical correction rather than through formal stress modeling. Measurement systems were standardized through cubit rods marked with subdivisions. Surviving examples display high consistency, implying centralized regulation of length units. Stable measurement permitted modular scaling and proportional planning. Proportional relationships in architectural layouts are observable, though interpretation of their theoretical significance remains debated. Repeated ratios can be documented, but evidence for explicit mathematical doctrine beyond procedural geometry remains limited. Water management infrastructure further illustrates engineering under environmental constraint. Basin irrigation required embankments calibrated to contain floodwaters at specific heights. Excessive height could reduce sediment deposition. Insufficient height risked destructive overflow. Nilometers measured water levels to inform expectations of yield and taxation. These devices structured observation and administrative response without formal probabilistic modeling. Grain silos were constructed to reduce moisture accumulation and internal pressure, their shapes distributing load to maintain structural integrity. The optimization problem was continuous. Align natural variability with storage, distribution, and labor systems to preserve administrative stability. Redundancy is visible in structural overdimensioning. Massive wall thicknesses, conservative load-bearing margins, and extensive foundations indicate tolerance for uncertainty. In the absence of formal equations describing stress, stability was achieved through scale, repetition, and margin. Standardization of components limited complexity during construction and reduced the risk that localized misalignment would compromise the whole. Administrative inscriptions sometimes record workforce organization and project duration, though interpretation of these figures is cautious. They nevertheless imply coordinated sequencing across multiple teams operating within shared measurement systems. The epistemic character of this optimization differs from later deductive geometry. There is no surviving corpus of general theorems and no explicit articulation of axiomatic foundations. Knowledge appears embedded in scribal training, apprenticeship, and institutional continuity. The archaeological record shows technical persistence across centuries, suggesting durable transmission of procedural constraint. Periods of political fragmentation coincide with reduced monumental construction, implying that institutional stability was necessary for maintaining engineering continuity. The evidence remains partial due to uneven preservation. Modern reconstruction of Egyptian mathematics and engineering is limited by fragmentary sources. Papyri represent a narrow selection of scribal material and may not encompass the full range of professional practice. Architectural interpretation depends on surviving structures, many incomplete or eroded. Claims of advanced theoretical abstraction beyond what is documented remain speculative. Conservative scholarship confines itself to demonstrable procedures and measurable results. Within those limits, Egyptian engineering demonstrates sustained alignment between calculation, material constraint, and administrative order. In this setting, optimization does not signify theoretical minimization or formal maximization. It signifies constrained sufficiency under environmental variability. Calculations ensure balanced distribution rather than ideal proportion. Structures ensure durability within known tolerances rather than mathematical elegance. Administrative systems prioritize repeatability, verification, and bounded error. These practices collectively indicate that rule-governed procedure can stabilize large-scale coordination without explicit deductive logic. The rules operate through measurement standards, modular design, verification routines, and institutional memory. As later traditions articulated geometry in axiomatic form, they abstracted from practices already stabilized through such constraint management. The Egyptian case demonstrates that consistent structural behavior can precede formal proof. Formalization would later reorganize these procedures into deductive systems, but the operational logic was already present in the discipline of measurement and construction. In the next episode, we will examine the I Ching, structured change without arithmetic, and its procedural organization of transformation. We will consider how structured variation can be stabilized without numerical calculation.